For this activity, we start by breaking things down in the subclasses first and then later move on to the main method. The first thing we do is to import Java util array class. This we'll use later when we start to convey our array into a string for easy display. Next, we declare our parent class called X for sorting, where we initialize an array. This array will be shared and used by the subclasses for sorting. The reason we do this in the parent class is to make sure that all subclasses are working in the same set of data, which keep everything uniform. After that, we create our first child class called merge sort, which extends from the parent class. Inside this class, we define a method named sort, which is responsible for triggering the merge sort algorithm. But before we run the algorithm, we first need to make sure that the array exists and actually contains element. That's why we add an if statement to check that the array is not null and not empty. Only when that condition is true do we proceed to execute the sorting process. Inside the subclass, we have two private methods, merge sort and merge, which together implement the merge sort algorithm. Merge sort follows a divide and conquer strategy. The array is first divided into a smaller part and then these parts are combined in a sorted order. The merge sort int L int R method is responsible for dividing an array into halves. The parameter L and R represent the left and right index of the portion of the array we are working on. Inside the method, there are base conditions if L is greater than R, which is ensured that we are only continue splitting when these are at least two elements. If L is less than R, that means that the subarray has either 1 or 0 elements, which are already sorted by definition. When the condition is true, the code calculates the middle index using nm equals L plus R minus L divided by 2. This formula is written in a way that avoids possible integer overflow, and it effectively splits the array into two halves. The method then makes the two recursive calls, merge sort L and M, to sort the left half of the array and merge sort M plus 1 R to sort the right half. Once the both halves are individually sorted, the method called merge LMR to combine them back into the one sorted portion. This is the key to step where the actual sorting takes place. The merge int L and M and R method is responsible for merging two sorted subarrays in one sorted array. The left subarray is R, L, M, and the right subarray is R, M plus 1, R. To do this safely, the method first calculates the size of these two subarrays, which have N1 equals M minus L plus 1 for the left side and N2 equals R minus M for the right side. Two temporary arrays are then created, L and R, to hold the element of this subarray. The next two loop to copy the elements from the original array into this temporary array, with L storing the left part and the R storing the right part. After copying three index variables are initialized, I equals 0 for traversing L, J equals 0 for traversing R. and key equals L for placing elements back into the original array starting from the left index. The merge process begins with a while loop that runs as long as both L and R have elements left. Inside this loop, the code compares the current elements of L and R, places the smaller of into R key, and increment the corresponding index. This ensures that elements are placed back in certain order. Once one of the subarray is exhausted, the next two while loop copy over any remaining elements from L or R into the original array. At this point, the segment RLR is fully sorted. In summary, merge sort keep breaking the array into a smaller and smaller part until each part contains a single element, while merge carefully stitch this part back together in sorted order. By repeating this process, the algorithm sorts our entire array efficiently. Inside this class, we have methods that work together up to perform quick sort, another divide and conquer sorting algorithm. While merge sort divide an array in the middle, quick sort instead chooses a pivot element and rearrange the array so that smaller elements go to the left of the pivot and large elements go to the right. Then it recursively sorts its sides. The process starts in the sort method. Here, we first check an array R if not null and has more than 0 element. If the array is valid, we call quicksort 0 R length minus 1 to sort the entire array from the first index 0 to the last index R length minus 1. The real work happens in the quicksort int low int high method. This method takes two parameters, low for starting index and high for the ending index of the subarray we want to sort. Like in the merge sort, we have a base condition. If low greater than high, if low is not less than high, it means the sub has 1 or 0 element, which are already sorted. If the condition is true, the method called partition, low-high method. Partitioning is the heart of quicksort. It chooses a pivot element, rearrange the array so that everything smaller than the pivot is on the left and everything larger is on the right. And then return the final position of the pivot pi. Once partitioning is done, the array has the pivot in its correct sorted position. The method then recursively sort the two sides, quicksort low pi minus 1 for the left side, and quicksort pi plus 1 high for the right side. But the partition in low and in high method is where the actual dividing happens. In this version, the pivot is chosen as the last element of the subarray. Pivot equals R high. An index variable is initialized to low minus 1. This I keeps track to the boundaries where elements are smaller than pivot should be placed. Then we loop through the array from j equals low up to j equals high minus 1. For each element, if rj pivot, we increment I and then swap ri with rj. Then ensure that by the end of the loop, all the elements smaller than the pivot are moved before I. After the loop, we place the pivot in its correct position by swapping Ri plus 1, high. Finally, the method returns I plus 1, which is the pivot finally sorted index. The swap int I int g method is a simple helper function that exchanges the two elements in the array. It uses the temporary variable temp to hold one variable, which whilst swapping the two position. In summary, quick sort works by repeatedly partitioning the array around pivot. Each partitioning step ensuring the pivot ends up in the correct sorted position, with the smaller element to the left and the larger one to the right. Then, the process applied recursively to the both sides. And we have here, inside the subclasses, we have the method that implement heap sort, another efficiently sorting algorithm. The process begins in the sort method, where we first check if the array R is not null, then has more than 0 elements. If it is valid, we call heap sort to perform the sorting. The heap sort method has two major steps. First, it builds the max heap from the array. The line of int I equals int divided by 2 minus 1 I is less than divided by 0 I minus minus heapify and an I. Start from the last non-leaf node and call heapify for each node moving upward. This ensures that the entire array now represents the valid max heap, meaning the large element is at the root index 0. The second step is the actual sorting. In the loop for int I equals n minus 1 I is less than 0 I minus minus. We swap the root element with the last element of the array. This places the largest variable and its correct final position. After the swap, we call heapify I 0 to restore the max heap property on the reduced heap. By repeating this process, each maximum element is placed at the end one by one until the entire array is sorted. The heapify int I method is responsible for maintaining the max heap property at a given node. Here, n is the size of the heap, which can shrink during sorting, and I is the index of the current node. The method starts by using the large value is an index I, and then calculate the indexes of the left child. L equals 2 times I plus 1, and right child R equals 2 multiplied I plus 2. If the left child exists within the heap, L is greater than N and is the correct largest, we update the largest to be L. The same check is done for the right child. If after this check, the larger value is not at I, we swap the element at I with the element at larger, and then recursively call heapify and largest to make sure the heap property is maintained through the tree. The swap int I and g method is a helper function that exchanges two elements in the array using a temporary variable. This is essential because both heap building and sorting depends on the repositioning elements. In summary, Heap sort works by first converting the array into the max heap, where the largest element is always on the top. Then, it's repeatedly remove the largest element by swapping it with the last element in the heap and shrinking the heap size. After restoring the heap, each time we heapify, the array is gradually become sorted. And we have here the last, the sort timer class, and it used to measure how long each sorting algorithm takes to run. In this time short method, the first clone of the array, so every sorting algorithm works very same data. And then record the same time, check which sorting algorithm is being used through the instance of operator and call the appropriate sort method. After sorting and finishing, let's record the end of time, calculate the duration, and print out both the runtime in nanosecond and the sorted array. In short, this class acts like a stopwatch and result the display for different sorting methods. In this program, the exercise for class contains the main method, which is served as the starting point of the application. Inside the main method, we first create a scanner object so that the program can take user input from the keyboard. Then, we use while true loop, which means the program will continuously run and prompt the user until the sorting choice is made. After the start each loop, we create a new object of X for sorting, which is provide us with the base array to be sorted. We display this array on the screen using array to string. So, the user can clearly see the current value before choosing the sorting method. After that, we we print out a small menu of options. When the user can choose whether to run, merge sort, quick sort, heap sort, or to display the time complexity comparison of all the sorting algorithm. Once the user entered their choices, we use switch statement to decide what action to perform. If the user chooses merge sort, we create a merge sort object, clone the original array into it, and then call the sort method to arrange the number. The same structure is followed for quicksort and heapsort. Each time, the program clones the original array into a new sorting object, prints, then unsorted array, performing the sorting and then display the sorted result. If the user chooses 4, the program creates a sorting time object, again cloning the array and the time how long each of the three algorithms takes to sort the array. This gives a clear comparison of their performance. Finally, if the user enters the valid option, the object simplify print the message telling them to try it again. That's all. And now we have parent class and the main class. We're going to run our file to see the output. Okay, wait a second. Okay, as a user, we choose 1, which is the first sort. Unsorted array 28, 6, 31, 12, 29, 26, 19. The sorted array 6, 12, 19, 26, 28, 29, 31. Now, if the user wants to choose the time complexity, how? You choose 4. Okay, as you can see here, heap sort is the fastest in the 3 of them. So that's it for our exercise number 4.